In this video we're looking at some features of geometric sequences. So we can see here a geometric sequence in front of us, and what defines a sequence to make it geometric is it goes up by a constant factor. In this case we can see that 2 multiplied by 4 gives us 8, 8 multiplied by 4 gives us 32, etc. So the factor of 4 is sometimes also called a common ratio. So for example, 8 divided by 2 is 4 and 32 divided by 8 is 4. Let's have a look at some definitions using sequence notation. We can see that the first term is 2, and the way we show that using sequence notation is we put the t for the term, and the green subscript 1 represents the position of the number we're talking about, and in this case the actual number is 2. Likewise, the second term, we've got a subscript 2 there in green, and the actual number, which is the second in the sequence, is 8. Let's have a look at the same sequence, but this time using a table. We can see here in blue that we've got the position of the number in the sequence, and in red we've got the actual number in the sequence. So for example, the first term is 2 and the second term is 8. Now looking further at the table, we can also see that each number in the sequence is found by multiplying the previous number by 4. So for example, 8 equals 2 times 4. Or in sequence notation, the second term is equal to the first term times 4. And likewise, 32 equals 8 multiplied by 4. Or again, in sequence notation, the third term is equal to the second term multiplied by 4. So there appears to be a pattern going on where we could say that any term in the sequence, we'll call it Tn, is equal to the previous term in the sequence, or in this case t subscript n minus 1, so in other words one less term, multiplied by 4. Now when we define a sequence like that, we have to be mindful that we know what the first term is, we can see it in front of us. But if we're defining it to somebody who hasn't seen the sequence, we need to give them the first term so we know where to start from in terms of multiplying by 4. So to give the entire definition, which is called a recursive definition, we say that Tn is equal to Tn minus 1 multiplied by 4, with the first term being 2. We can also define that another way by saying any term in the sequence multiplied by 4 gives the next term in the sequence, or in sequence notation, Tn plus 1 is equal to Tn multiplied by 4, where the first term is equal to 2. Let's have a look at another way to define the sequence, and this time what we'll do is we'll start by looking at the first ratio, which is each number in the sequence divided by the previous term. We can see here that it's a 4. So building on this, to form our rule, we're multiplying by 4 every time we want to find a new term in the sequence. So we're looking at powers of 4 because that describes multiplying by 4 multiple times. So we've got here the powers of 4, 4 to the 1, 4 squared, etc. And we know that they come to 16, 64, etc. as well. So we know the first term is 2, the second term is 2 multiplied by 4, and the third term is 2 multiplied by 16. We can describe that as powers of 4. In other words, we have 2, and then the next term in the sequence is 2 multiplied by 4 to the 1, and the next term in the sequence, 32, is the same as 2 multiplied by 4 squared. So we can see a common thread in the numbers in the sequence. What's happening is that each term in the sequence is 2 multiplied by 4 to some power, where the power is 1 less than the actual position in the sequence. For example, we know that the third term is equal to 2 multiplied by 4 to the power 2. The power 2 is 1 less than 3. We can put that into a rule. We can say that any term in the sequence, Tn, is equal to 2 multiplied by 4 to a power where the power is 1 less than the position in the sequence. Or using symbols for geometric sequences, we can say that any term in the sequence is equal to a, which is the first term, multiplied by r, which is the common ratio or the factor that we multiply by each time, to the power n minus 1. So let's have a look at how we use this rule to find any term in the sequence. In this case, we want to find the 12th term. So we substitute our numbers into the rule. In this case, a is representing the first term, which is 2, and r, the common ratio, is what we multiply by each time, so in this case it's 4. And because we want the 12th term, n minus 1 will become 12 minus 1, or 11. So multiplying this out, we get an answer of 8,388,608. So now let's have a look at another problem where we've got to find the actual position in the sequence to find the first term to exceed 50 million. So what we'll do is we'll go to our rule for geometric sequences, which we can assume each time if we know the sequence is geometric. And in this case, of course, it's being multiplied by 4 each time, so we're safe to assume that it is a geometric sequence. And what we'll do is we'll substitute 50 million in for Tn, because that's the term that we actually want. We know the first term is 2, and we know that the common ratio, what we multiply by, is 4. So we're trying to solve that equation. And the easiest way to solve that equation would be to substitute it into our calculator and go through and solve using an equation solver, and we get n equals 13.29. Now we can have a 13th term in the sequence and we can have a 14th term, but it doesn't make much sense to talk about a term which is in position 13.29. So we know because the sequence is increasing that the 13th term will be slightly under 50 million and the 14th term will be slightly over 50 million. So the first term to actually exceed 50 million will be the 14th term.